Welcome to class. In this video, we're going to talk about variation of parameters on systems of ODEs. Let's get started. Recall that every first-order system of ODEs has n fundamental solutions, where n is the number of equations. Those fundamental solutions, as I've labeled u1 through un up here, are all linearly independent from each other. So building a general linear combination of them is what we call the general solution. For the ODE, the principle of superposition tells us that this will also be a solution. Now I can actually write those, in the case I have a system, as a matrix times those coefficients, or those parameters from my problem. When I write it this way, that matrix, capital Phi, is called the fundamental matrix of an ODE. And this looks very archaic or cryptic, but it's actually a pretty straightforward process to find one. So let's do a quick example. So here's an example of a first-order homogeneous system of equations. dx dt is x plus 3y, and dy dt is 3x plus y. Now, to clarify here, when I write this in matrix form, say as u prime equals 1, 3, 3, 1, u, this matrix is not the fundamental matrix. That's the one that defines my system. The fundamental matrix is essentially just a different way to write the general solution. So I still need to find the general solution. Turns out the eigenvalues of this matrix are 4 and -2, with corresponding eigenvectors 1, 1 and -1, 1, respectively. This will let me write the general solution as C1, V1, e to the lambda 1 t plus C2, V2, e to the lambda 2 t. But I could just rewrite this whole thing as a matrix. It is, if I distribute my e to the 4t's in, e to the 4t, e to the 4t, plus C2, negative e to the negative 2t, e to the negative 2t. And notice this almost looks like a matrix product. I can rewrite this as e to the 4t, negative e to the negative 2t, e to the 4t, e to the negative 2t, times C1, C2. I wrote it as a matrix times the column vector of parameters. But do you notice anything about the construction of our fundamental matrix? It's just the eigenvectors. So really, at the end of the day, the fundamental matrix for a system of ODEs is just the matrix composed of the eigenvectors of A. As a quick refresher for the game plan on variation of parameters, when I had a first-order non-homogeneous linear ODE, I assumed the trial solution would have the form CE to the something t, lambda t, where that lambda was determined by the complementary equation. But instead of taking a constant parameter, I allowed my parameters to vary. And so we assumed that the particular solution had the form some function of t, which we called mu, times e to the lambda t. If that doesn't at all sound familiar to you, check out the variation of parameters videos that I have linked in the description. But how do we extend that idea into higher dimensions when I have an n by n system? Well, the idea is still the same. The complementary solution we can find and express using the fundamental matrix. It's phi of t times my vector of parameters. But now I need to let that vector of parameters vary into a vector field, mu of t. Then I want to plug this expression for the particular solution back into the ODE. If it's a solution, it should satisfy this equation. That might help us determine mu. Let's do it. Just made a little bit more room here. If I'm going to plug yp in, I'm going to need to know its derivative first. Remember, taking the derivative of a vector-valued function with a scalar input is equivalent to just differentiating each of its entries, and the same goes for matrices. So when I go to take the derivative of yp, I use the product rule as you might expect it, where I take the derivative of the first times the second plus the derivative of the second times the first. Just here paying close attention that the order in which we multiply those things matters. Now, when I plug that into the right-hand side, I get a times yp, which is phi mu, plus f. Now recall that phi is the fundamental matrix for the system, which means that it solves the complementary equation. But I have a phi prime here. To show those loose ends a little bit more carefully, phi prime, since it is the complementary solution, is equal to a phi. And I'm going to make that substitution here to write this line. And you'll notice that I have an a phi mu that cancels from both sides. And now I have a single variable equation, that variable being mu prime. And solving for mu prime, remember I don't really divide by matrices, instead I multiply by their inverses. So when I multiply on the left by phi inverse, I get that mu prime is equal to phi inverse f. Now, the last step would be to integrate to find mu, because this is a separable equation. This tells me that mu of t is equal to the integral of phi inverse f dt. Taking a matrix times a vector will produce me a vector, an n by 1 column vector. And integrating that vector-valued function is equivalent to just integrating each of its components. So in this way, we have found a way to determine the particular solution. Yp is mu times phi, or phi times the integral of phi inverse f with respect to t. So, if we want to apply variation of parameters to this problem, we first need to build the fundamental matrix, phi, which of course is just the fundamental solutions in each corresponding spot. So here I've got a 1 e to the 4t, I've got a negative 1 e to the negative 2t, I've got a positive 1 e to the 4t, and I've got a positive 1 e to the negative 2t. And as we just saw, the particular solution is phi times the integral of phi inverse f. So let's build this up piece by piece. First of all, phi inverse is, and if you need a quick refresher, by the way, I've linked a good video on how to compute the inverse of a matrix down in the description here. But it ends up being, for our problem, 1/2 e to the 4t, e to the negative 4t, negative e to the positive 2t, and e to the positive 2t. Now, when I multiply that by f, I should have a 2 by 1, and I get 1/2 times e to the negative 4t times the polynomial negative 2t squared plus t plus 5, and e to the 2t squared plus t plus 5. I integrate that guy. With respect to t, and I end up with the matrix, or the vector, excuse me, 1/2 of 1/4 e to the negative 4t times 2t squared minus 5, e to the 2t, t squared minus 1/2 t, plus 11 over 4. Last but not least, I multiply my original phi by this integral to get the particular solution. And wouldn't you know it, here's what I land at. That's what we found through variation of parameters. Excuse me, through method of undetermined coefficients. This is variation of parameters. So, like I said, you can really use either method you'd prefer, just whether you prefer doing more calculus or linear algebra, I suppose.